So the main topic that we're going to be covering in this class and the main theme of everything is now what happens when we add in another variable. Okay, and we want to work up to adding several different variables, but we're just going to focus mostly on when we have two independent variables and one dependent variable, meaning that we have a function of two variables. So with three total variables, with the two independent and the one dependent, we're going to need a three-dimensional coordinate system, right? So up to this point, we only had a two-dimensional coordinate system, right, where we have our x-axis and our y-axis. Should be very familiar with this at this point, right? But I'll just go ahead and draw it for reference. Okay, so something like this. So now we want to open this up to 3 dimensions. So this is where it's going to get kind of tricky to hand draw this stuff. And I'm going to use, three-dimensional calculating tools wherever I can, like the GeoGebra, however you pronounce it, that I showed in some video in Math Tools 2. And there's another 3D calculator we can use if needed, and I'll link to those on the discussion board, of course. But for now, let's just try to kind of show how we represent this by hand, because these are commonly drawn by hand still. Okay, so this is the two dimensional graph. So if we're going to extend this out to 3 dimensions, here's what we typically do. So we typically will draw the y-axis over here. So what we're basically going to do is imagine that we take this 2-dimensional graph that we have, and now imagine that we're looking straight down at it. And then we make another axis coming out of the page at us, or out of the screen at us, right? And then we're going to rotate that a little bit. Okay, so with that, the y-axis ends up down here. Going straight up, which would be the one coming out at us, how I just described, this is what we call the z-axis. And then going this way, so now we've rotated it, so this is kind of now the one that would be actually coming out at us. This is going to be our x-axis. Okay, and these are all the positive parts of the x, y, and z axes. So this would be 1. This would be 1. And this would be 1. And then to represent the negative axes, we use dotted lines or dashed lines. Okay. And this is common to use dashed lines when you're trying to represent three-dimensional things. But you can see it's hard to represent, especially when you're not artistically gifted, like myself. Okay, so this would be like -1. This would be like -1. Here we'd have a -1. Okay, so if we wanted to graph the point, let's say like 2, 3, 4, the way we read these is as an x, y, z ordered pair. Okay, so we'd go to 2 on the x-axis, 3 on the y-axis, and then 4 on the z-axis. And you can see why it's hard to represent this, if not impossible, right? There's really no way to tell where this is on the x-axis. So it's very difficult. So for that reason, if we are hand drawing it, it's a good idea just to label the point. Okay. Now I'm going to switch over to the 3D graphing calculator here. So this is GeoGebra. So this is one that that I like. There's another one right here called math3d.org. So I don't know which one of these I'll use most next. Let's actually use this one for right now, since it does have the grid here that you can see. But but they're basically the they should be able to do all the same stuff. Okay. But anyway, and this one has the axes labeled, as you can see, right? So here's the x-axis, here's the y-axis. Yep, there's the z-axis. If we zoom out a little bit. So the middle here, we still call the origin. So that's the point 0, 0, 0. It's also divided into octants, 8 different areas, just like the two-dimensional graph is divided into quadrants, 4 different areas. So we can kind of see the two-dimensional graph still in here, right? If we rotate it and then bring it upwards, we can see we have our normal XY graph, right? So we're just moving this around a bit. So we have the 8 octants. So octant 1 would be the place where X, Y, and Z are all positive. So, you know, kind of in this general region here, etc. So we won't really refer to the octants like we would to the quadrants. Not that we even really did that too much. Generally, to orient yourself on the graph, you follow what's called the right-hand rule. So the right-hand rule is where you position your hand so that it's in line with the x-axis. So the way it is right now, if you held your hand straight out towards the screen, it would be in line with the x-axis. And then you curl your fingers towards the y-axis. Wherever your thumb is pointing is the positive part of the z-axis. Okay, so that's called the right-hand rule, and it lets you orient yourself to see which direction all the positive axes are. So again, you put your hand straight through the x-axis, curl your fingers towards the y-axis, and then wherever your thumb is pointing is where the z-axis will be. Okay, so that gets a lot more use in physics and stuff, where you're kind of like, you know, kind of like moving the coordinate system around a lot more. Here we're going to have it pretty static, so it won't be too big of a deal here. So let's see if we can add a point on here. So I'm not super familiar with this one. Kind of learning as I go here. I've used GeoGebra a little bit more, but I just like that this one has the grid on it. So let's see, if we put 2, -2, 1, we can see that it fills in here, and then we can rotate it to kind of get a sense for where exactly it's oriented. Okay, so that's helpful. So note, if you put 0 on the z-axis, then it just becomes like a normal point, basically at 2, -2. It's kind of hard to tell because it's not like lined up perfectly, but it should be lined up with 2 and -2 here. This little tick mark right here might be a little hard to see. So we can also talk about the different subsets of this graph, which is that there are 3 different planes we can talk about. We have the XY plane, as we can see here. So this is known as the XY plane. We have if we flip it around a bit, we have the YZ plane. So it doesn't have the grid here, but same kind of idea. And then we also would have the XZ plane, if we'd like. I guess this would be it, right? So we have the XZ plane as well. So there there's kind of like 3 different 2-dimensional coordinate systems that are built into this one 3-dimensional coordinate system. So if you play around with this a little bit, like if you can see vectors are in here. I don't know how functions work, but if we were to try to put like a 2-dimensional function here, so something like that's a function of x and y. Yeah, nothing's coming up, so I'll have to look at that for a separate video, but you can try to start graphing some 3D functions here. I'll show it in GeoGebra just to show what it looks like. So back over in GeoGebra here, so if you just put an expression in here, like f of x comma y is equal to e to the x. So what does this look like here? So we don't actually have a y variable. So notice that this looks like the e to the x function, but you just have like infinite number of copies of it basically. So it turns into this plane. So if we looked at it perfectly from the side here, which I don't know if I can orient it perfectly, it looks like e to the x. It's backwards because I have this backwards, but yeah. So if we look at it perfectly from the side, it looks like the function e to the x. I can't really get it. There we go. But then we open it up and we see actually it's a plane. Okay. And then of course we can add in a y part as well. And now it's kind of tilted inwards. Okay. So this is this kind of stuff is this kind of like 3D graphing, of course, would be really important in something like physics, where you're trying to model the real world. Let's see if we can change here. So this is what a parabola would look like, right? X squared plus y squared. If you look at it from the top, it looks like a circle, which shouldn't be too surprising. This is the formula for a circle. X squared plus y squared, right? Equals some radius squared. So any cross section of this would be a circle, which is something that similar to an idea we talked about in Math Tools 2, right? The cross sections, how we would find the volume of objects like this. All right, so so going back onto this one here. So if we add another point here, so this one's at -2, 2, 0. If we add one at say like let's say like -3, whoops, -3, 1, 2, something like that, then we can see where these points are kind of oriented with each other. So we had the distance formula in the two-dimensional system, and we'll have something similar here. We'll have another distance formula. So let's look at what that would be. Okay. It's pretty much exactly what you would expect. I won't go through the whole proof with the Pythagorean theorem and all that because it's a little bit more complicated in 3 dimensions, but it extends very naturally. Okay, so the distance formula with 3 dimensions here would be that the distance is equal to the square root of x1 minus x2 squared plus y1 minus y2 squared. And now we add on this extra part plus z1 minus z2 squared. So that's all. So we just add in this extra component here. So basically we just add on the distance between the two z components. So in the example I just had written out here, we have -2 or 2, -2, 0, and -3, 1, 2. So to find the distance between these, we would do 2 minus -3 squared, so 5 squared, plus -2 minus 1 squared, so -3 squared, 0 minus 2 squared, so 2 squared. So we get 25 plus 9 plus 4. So what's that? Square root of 38. Okay. Which will be a little bit more than 6 if we want an approximation there. Okay. So, you know, it's obviously hard to kind of actually do that, but it should make sense that this is about 6 units away, right? This one, just on the XY plane alone, you know, you can see that they're just going horizontally, they're, you know, 5 units away. So the going on an axis like this is of course going to add to it. So 6 definitely seems like a reasonable answer there. So other things will typically extend pretty nicely as well. Like for example, the equation of a circle. is, in general, it's x minus a squared plus y minus b squared equals r squared, where the center is AB, right? And r is the radius. So a sphere then extends pretty naturally as well. You get x minus a squared plus y minus b squared plus z minus c squared equals r squared, where the center is then A, B, C, right? So just to show that, a lot of these things will extend kind of naturally. And that's kind of the theme, is like, when we look at derivatives, they'll extend pretty naturally into the third dimension. When we look at integrals, they'll extend pretty naturally. Same with limits, all that kind of stuff. But of course, there will be certain caveats and certain unique circumstances that will be introduced by this new dimension that were kind of masked by being in a two-dimensional system before, that we will have to pay attention to.